All right, let's go ahead and get this going here for the last part of 3.3. So here we're asked find an equation for a line that is tangent to the graph y equals e to the x and goes through the origin. So essentially here in blue, you can see here is the function y equals e to the x. That's it right there. And then we're trying to find an equation for this line right there that goes through the origin and is also tangent to the function. So any other line that may be tangent to this is not going to go through the origin. It's going to go through somewhere else or somewhere over here. So there are basically an infinite number of lines that are tangent to this function, but they do not go through the origin. So we need the one line that is both tangent and goes to the origin. And if you remember from last time, earlier in this section, we found that when we have the function f of x equals e to the x, its derivative is pretty much the easiest derivative to do. It's just e to the x. All right? And so that makes it pretty simple there. Now, if we call the location where this graph is going to be tangent, we're going to label that as the point A, and then it's going to be the y value e to the a. So if this equals our slope as a function of x, essentially, right? That means our slope at point A is just e to the a, where x equals a. Now, using that, we can say that we've got to have y equals mx plus b. That's the equation for a line. We know that this is going through the origin, so the y-intercept is 0, so we just need y equals m times x. And we know that m is just e to the a. So we know that our function must be e to the a times x. So the only thing we really need to do now is figure out what our a value is. So if we come here and we look at the point a e to the a, we know that if we plug it in, right, if we plug this in, we get that e to the a equals e to the a times a. And the e to the a's will cancel, and that'll leave us with just a equals 1. And therefore we know that a equals 1, and we can come down here, plug that in, and we get e to the 1 times x. So our function is y equals e, Euler's number, times x. And that right there will be the equation for our red line there that is tangent to e to the x and goes through the origin. Okay, so let's try the next page here. So on the next page, we're going to start to talk about derivatives of products. So let's look at these two derivatives that we have here. The first is the derivative of x times x, which is just the derivative of x squared, which we've done before with our power rule, and that's just going to bring the 2 out front and then multiply it by x to the 2 minus 1, which is just x to the first power. If we look at the second one, the first thing we have is the derivative of x, which is just 1, and then we have the derivative of x, which is just 1, and this equals 1. And so these two things do not equal each other. So be very careful, because the reason you're getting showed this is you might be tempted to distribute this derivative through onto each x, right? Like, but you don't want to do that, because if you do that, you're going to end up getting it wrong. Basically, what I'm saying here is you cannot, or a derivative cannot be broken over a product. You can't do that. All right, that's not going to work. You're going to get it wrong, so don't do it. So what we need is a rule for how do we do derivatives of products. How do we actually kind of like distribute it through like that? And this is our rule right here. It's if u and v are basically they're differentiable functions at x, so it's like u is a function of x, v is a function of x, shorthand for it. So the derivative of u times v is equal to u times the derivative of v plus v times the derivative of u. In prime notation, that's u times v prime is u v prime plus u prime times v. All right? In function notation, the derivative of f of x times g of x is the derivative of the first function times the second plus the first function times the derivative of the second function, just like that. So, say it in your head a few times, derivative of the first times the second plus the derivative of the second times the first. Just like that, and you'll get it down. I also want to point out that this rule is actually pretty useful in a lot of places. For example, if I wanted to use this rule, say I didn't realize that the derivative of a constant times a function is simply, we know this from before, we could just move the derivative past the constant. We could break it in between this, but we don't have to. All right, this would just be c times the derivative of f, but what if we applied the product rule? Say we were having a bad day or we forgot about that rule. Well, it's okay, it'll work out for you. So let's do the derivative of the first function. Our first function is c, so the derivative of c times f of x plus c times the derivative of f of x. And if you did this, you'd see that the derivative of c, this is the derivative of a constant, so that's just 0. And so this whole first part is just 0, and all you're left with is the constant times the derivative of the function, which is what we had come up with before, and so even using the product rule there works. And if you came back up to this first example up here, when we were looking at that, if you apply the product rule, leave it as x times x, and apply the product rule, you'll still end up getting 2x. You just don't want to split it like that. Don't do that. Okay? I mean, if you're given this problem, then do it the way I did it. But if you're given this up here, don't turn it into that. Those are not equal. All right, let's take a look here. Let's try some examples of using the product rule. Just so we have it, I'll go ahead and write it here. d dx of f of x times g of x is the derivative of the first times the second plus the derivative of the second times the first. So just something like that. And now I think I flip-flopped the order on these two, but that doesn't matter because they're just multiplying together. So I think on the other page I wrote f of x times g prime of x, but don't let that confuse you. That doesn't matter. So here we go. Let's try this first one. We're going to say that f of x equals 1 over x. Now when you're first doing these, you're probably going to want to write them out like this, but if you get good at them and you get better at them, you'll probably stop doing this, but g of x is x squared plus e to the x. So you look at it and say these are my two functions. The first one, the derivative of this, well, remember 1 over x is just x to the negative 1, which means we can use the power rule here. We can bring that negative 1 out in front and make it x to the negative 2 like that. For g of x, g prime of x is going to be the derivative of the first term, which is 2x, plus the derivative of the second term, which is just e to the x. Then we just need to combine them together. So y prime is going to equal the derivative of the first, so f prime of x, that's this right here, that's negative x to the negative 2, times g of x, so that's this right here, so times x squared plus e to the x, and then plus the derivative of g, so that's this right here, that's 2x plus e to the x, and then that's times f of x, which is just this over here, or actually I'll probably just put it as this one, x to the negative 1, just like that. Now remember, we can take this and put the negative sign with the x squared plus e to the x on the first term here, and then divide it by x squared. That's from this x to the negative 2 is 1 over x squared. And then similarly over here, this is 2x plus e to the x over x. So be sure you can recognize that those two, that the negative exponents become divide bys like that. All right, so let's take a look at this one. Y equals y equals e to the 2x. Here, what I'm going to do is I'm going to let you try this one. And this is just going to be e to the x times e to the x. So try applying the product rule to that, and then see how it goes, and I'll put the answer for you in the notes to take a look at. Same thing on this page. I'd like you to try this one. This will be the function f of x. This is the first function. This is the second function, g of x. So give that a try, see what you get. Then what I want you to do is actually, so do this first. So do it just like this using the product rule. So do it with the product rule, and then go back and actually multiply this out. So this would be x squared times x to the third, that's x to the fifth. X squared times 3 is 3x squared. 1 times x to the third is x to the third, and then 1 times 3 is 3. So what I'd like you to do then is go through and do this just using the power rule. And I want you to try both ways, and I want you to see if you get the same answer either way you do it. You should get the same answer. If you don't, then you've probably made a mistake in one or both of the methods. So give it a try and see if you get the same answer. And again, I'll put the answer and the, my work out in the notes for you to look at. All right, what do we do with quotients? What if we have a function u and a function v, and we have u divided by v, and it's differentiable? So in other words, v is not 0. How do we find this? And this is it right here. It's very similar in the numerator to the product rule, except it's a minus instead of a plus right there. And then we just divide it by whatever the denominator is squared. Now, if you don't like this and you think, man, this is going to be kind of a pain, this is pretty complicated, there's a couple of things. One, you don't actually have to use this. In a bit, we're going to learn something called the chain rule, and when you have the chain rule and the product rule, which you're going to have to know both of those anyway, you can always use just chain rule and product rule to do any quotient ones you come across. That's typically what I tend to do. Or you can memorize it. There are some things like some students told me this. I've never really had this very useful for myself, but they seem to like it. Low D high minus high D low over the square of what's below. So I don't know. I never remember that. I had it written down here before I did this video, but that's what some students tell me helps them. Low D high minus high D low over the square of what's below. So if that helps you, go for it. If you want to see this in function notation, it's d dx of f of x over g of x, like that. And then this is g of x times f prime of x minus g prime of x times f of x all over g of x squared, like that. Okay, so let's try and do one here and see how it goes. So our f of x is going to be what's on the top, so f of x. And again, once you get good at these, you will probably stop writing this out in so much detail. This will be t squared minus 1, and then the derivative of that is going to be the derivative of t squared, which is 2t, and the derivative of minus 1 is just 0. G of x is going to be t cubed plus 1, and that's going to be g prime of x equals 3t squared, and the derivative of 1, again, is 0. So we can combine these together just using our little formula up above. So we've got, we're going to have g of x, which is just t cubed plus 1. So that's this, times the derivative of the numerator, which is 2t, minus the numerator, t squared minus 1, times the derivative of the denominator, 3t squared, all over the denominator, t cubed plus 1, squared. And you can go through, just so this video isn't super long, you can go through and reduce this down, do a couple of lines, and you should get that you can get something like negative t times t cubed plus 3t plus 2 all over this t cubed plus 1 squared. Okay, so you can get something like that. Now looking at this one, you think, well, this isn't in any kind of a quotient, but it's e to the negative x, so that's 1 over e to the x, which means f of x is 1, and the derivative of 1 is 0 because it's a constant. Derivative of a constant is 0. That's the slope of constant lines. G of x is e to the x, and the derivative of e to the x is e to the x. And so we simply go from there and start putting it together. So we've got the first function, e to the x, times, right? This is our denominator, times the derivative of the numerator, so times 0, so that's 0, minus the derivative of the denominator, e to the x, times the numerator, which is just 1, all over the denominator squared, e to the x squared. And so this is just negative e to the x over e to the x squared. So this e to the x will cancel with one of the e to the x's in the denominator, and we're left with negative 1 over e to the x, which is just negative e to the negative x, whichever way you want to write that. But you need to recognize those are the same. Okay? You need to be able to tell that those two are the same, and whichever way you want it, especially if it's multiple choice, you need to recognize, because you're not going to get both of those answers. You'll just get one or the other. And if you didn't come up with the one that they show, you need to recognize that that one's there. All right. This one I'd like you to try on your own. I will put the answer in the notes for you after I'm done with the video. Next, same thing here. Try this one as well. You're going to find some points on the graph y equals x over x minus 4 with tangent lines perpendicular to the line y equals 4x minus 3. So in other words, if it's going to be perpendicular, right? Remember, perpendicular means the slope is the negative reciprocal of the slope of the other line. So if lines are perpendicular, their slopes are negative reciprocals of each other. So just to get you started off here, the slope of our original line right here that we want it to be perpendicular to is 4. Therefore, we need lines with a slope. So we'll call this like slope original and the slope perpendicular. The perpendicular slope is the negative reciprocal. So you need to find all the points on that function where the tangent line has a slope of negative 1/4. So give that a try. And again, I'll put it all worked out for you in the notes. Next, we can take derivatives of derivatives, usually, not always, but if y equals f of x is a differentiable function, then its derivative, f prime of x, is a function. If f prime of x is a differentiable function, then its derivative, we call it f double prime of x, is a function. And that's supposed to be just two little primes there. The function f double prime of x is called the second derivative of f. The notation for this is f double prime of x, y double prime, or d2y over dx squared. Notice the 2 comes after the x here, but it comes after the d in the numerator. The reason for this is we can actually write this as the derivative of the derivative of y, like that. And then we can combine these derivatives together. And like I told you before, this is like an algebraic thing here. The dy dx is like algebraic. That gives us a d squared in the numerator and then a dx times dx in the denominator of y, like that. Dx times dx is dx squared, dy d squared, and this is operating on the y. So the operator is actually just the d squared by dx squared, like that. d2 over dx squared. So it's important that you get that notation down, that it looks like that. That's the actual operator. This is the function that's being operated on. Similarly, if f double prime is differentiable, its derivative, f triple prime of x, is the third derivative of f. This process continues, and you can continue it until you can differentiate no further, which is what the nth derivative is. After the third derivative, you start listing things like this. You don't write out 1, 2, 3, 4 of these like that, especially if you're doing like the 20th derivative. You're not going to want to do that. Instead, what you do is you put what derivative is in parentheses like that after the third derivative. Up to the third derivative, you're fine with just 3 little slashes, 3 little prime symbols. But after that, you put it like that. And this is the fourth derivative. And then you can, keep going on to the nth derivative. Now, some functions, after you take a few derivatives, it's going to end up being 0, like x cubed becomes 3x squared, becomes 6x, becomes 6, becomes 0, 0, 0, any other derivatives you take. While other functions, you can do this an infinite number of times. For example, e to the x. The derivative of e to the x is e to the x. The derivative of e to the x is e to the x, e to the x, e to the x. And it's just going to continue on like that for an infinite amount of time to do it. So here, let's try an example. This is find the derivative of all orders. So keep going until we basically reach a 0. And so we're going to do y prime. Derivative of x cubed is 3x squared. Derivative of negative 3x squared is negative 6x. And the derivative of 2 is 0. Then we can do the next derivative. 3x squared becomes 6x minus 6. Derivative of 6x is 6. Y triple prime, the third derivative. Derivative of 6x is 6. Derivative of negative 6 is 0. And then the fourth derivative is just derivative of 6 is 0. All right? And, you can go on so and so forth just like that doing these derivatives. And again, for example, like that e to the x, we could do like, say you were asked something like derivative, the 76th derivative dx to the 76 of e to the x, something like that's going to be easy. That's just e to the x. Okay? So, just go ahead and be careful with that. One more thing I want to point out here is if you have taken, if you've ever taken physics, you would have learned something, an equation maybe that looks something like this, 1/2 at squared plus vit. And this is what is called the kinematic equation of motion. Sometimes it's written as S equals 1/2 dt squared plus v naught t. There's different things, S's and D's and X's and v naughts and vi's and all kinds of stuff. But for the basic part, this is position, this is acceleration, this is time, this is your initial velocity, that's time again. And what you would find, if you've seen these before, is if you do the first derivative of this, we can actually write this as delta x. That's x final minus x initial, like that. That's what delta x is. Okay, that's this part. And I can put that xi over. I'll get xf equals 1/2 at squared plus vit minus x final, which is just a constant. This position where you ended up. Okay? If I take the derivative of this, a time derivative, d dt, derivative with respect to time, I get dx, oops, this should have been xi, starting position, sorry, xi. I get derivative of your final spot dt, which is just going to be your velocity, which is your rate of change, so it's just velocity, rate of change of your position, equals 1/2 at squared. So the derivative of t squared is 2t, and so 2 times a half is just that, so it's just at. 2 times a half is 1, so it's at, plus derivative of t is just 1 plus vi. And you may recognize that. So you should recognize this. This would be one of the kinematics given to you. This one down here, this is the second kinematic given to you. Do another time derivative of it, and you get dv dt, which is our acceleration, which is our second derivative of our position. And that's our acceleration. And then the derivative of a times t is just a, and the derivative of vi, which is a constant, is just 0. And this just tells you a equals a. So what this tells you is that this equation here in physics and this equation here are valid if the acceleration just always equals itself. In other words, if it equals a constant. Constant. Okay? So just a little something for you if you've taken physics or you're about to. That will help you with it. Okay? Maybe. So you can memorize those equations a little better. They're just derivatives of each other. All right, so that brings us to the end of this section. Be sure to look back in the notes to see those worked out problems that I wanted you to work on your own. All right, that's all.